ACH. And if ACJ is shorter than ACIJ, so we have to compare these two things, and to see if we have to update the distance from the starting point to any adjacent node. So let me give you another example. So in this example, I have a graph. And this is the starting point. And we label this starting point as 0 because from this point to this point is 0. And we have the weight on each edge or each link, 5 to 8. And in the first step, we can say that starting from this shortest path tree, which contains only one node, the distance from it to adjacent nodes are set respectively 5 and 8. 5 and 8. So we have a shortest path tree containing one node, and we have two adjacent nodes. And from the starting point, we have two branches. But these two branches are not the shortest path tree. Only one of them is selected into the shortest path tree, will be 0 to this node. And the weight of that node will be 5. And after that, after we select this node into the shortest path tree, we update all the adjacent nodes of this node, newly selected node. Then we get the weight of these, and that nodes. And similarly, we do that until the whole network is explored. So, do you have any question about this? In optimization, they often call it label correcting algorithm. So each time you select a node into node set 1, and then you update this label, which means the distance from the start node to this node. So it's called label correcting algorithm. But I prefer to call it dexterous algorithm. Are we really clear about this?
What does the blue links in the last graph?
Which one? This one?
And the last one.
This
is
blue?
the shortest path tree.
Let me think. That's a good question. I haven't paid attention to these things. Let's see.
Yes, it is.
I think it is.
Yes.
Yes, it's the shortest path tree. Final shortest path tree is that there. Yes. So for example, this is a temporarily shortest path tree. No. This is temporarily shortest path, but it's not in the shortest path tree. Only the nodes that are gray can be confidently set as shortest path tree. I mean, these nodes are in the shortest path tree, and the links between them are the shortest path segments. But in this case, this node is not explored yet, or this node is an adjacent node. This node is shortest path node. So the link between them is not 100% sure to be in the shortest path tree. Are we clear about this?
And that tree is a unique tree, a unique solution?
Yes. I cannot say it's unique solution because sometimes there may be two paths with the same weight, with the same distance. It's possible. So this shortest path tree will not be the unique. But there will not be any path that's shorter than this. So there may be several shortest path tree existing. Do you have any questions? Because this is the most important thing. And if you don't understand this at this moment, please ask. Otherwise, it will take you too much time in the homework, which you shouldn't spend.
What is the red circle and the yellow circle?
The red circle is the node that is recently added to the shortest path tree. So in this part, before this picture, before this step, all the nodes are white. And the first node to be added to the shortest path tree is this node, because it's directly connecting to the front node, or it's actually the front node. And then in the next step, it's adding this node to the shortest path. Starting from this and add this. Or in another word, the yellow node is a node that was previously added. The red node is a node that is currently added. So 2 steps. I think 1 step is missing between that graph and this graph. Okay, but you can do it by yourself. So do you have any question about this? Because in today's homework, if you already understand this, it will be very quick. It will take you only 5 minutes. Otherwise, it may take you 1 hour. So for the time complexity of this algorithm, let me give you a very important tip. For a large network, if A is the total number of links, if B is the total number of nodes, then their relationship can be roughly estimated by the number of links is 2.5, the number of nodes. So they are of very similar magnitude, okay? For the Dijkstra's algorithm, a naive implementation which uses ordinary linked list or an array, which these are data structures you may not have learned. But in a naive implementation, the time complexity is equal to A plus B squared. And this is dominated by B squared, right? Because it's squared. So it's O(n) squared. I want to interrupt this thing by mentioning that shortest path is always solvable. Or if you are using the naive search or exhaustive search, you can get it. Dijkstra is only an optimized method, but that brings a lot of benefit. So in the future, if you read a paper, and this paper presents a new shortest path, and if this paper is not from computer science, sometimes you are not going to see the analysis of time complexity. If there is no time complexity, just discard this paper. Because we have solutions, we need faster solutions. We don't need new solutions that are slower, okay? So in a naive implementation using linked list or array, the time complexity is O(n) squared. But if we use binary heap or Fibonacci heap, these are advanced, some other data structures I'm not going to introduce, we can reduce the time complexity to something A plus B log B. And this part is dominating, so in short, the time complexity is O of n log n. Remember this. This is the time complexity of Dijkstra's algorithm. N is the number of nodes. Okay, remember this. You don't need to develop to derive this, but remember. Now, the third topic of today is the application of shortest path in transportation. The first topic we want to talk about is time-dependent link delay. What does this mean? This means that from one node to another node, there is a basic travel time, base travel time. But if you travel at a different time period, the delay will be different. So for example, sometimes it's very congested, so you have longer travel time. And in this case, how can we calculate the shortest path? The second problem is called K shortest path, or sometimes it's called the second shortest path, or the alternative shortest path. This is very useful in traffic assignment because we can, initially we assign all the traffic to the shortest path. And then it will be very congested on that path. But there may be some other paths people will use. So that's why in traffic assignment, dynamic traffic assignment, they always want to find several paths from A to B. And this can be called shortest path. It has been proved that k shortest path is much harder than one shortest path. For example, how can you, if you already know the shortest path, how can you create a second shortest path? An usable second shortest path. Let me give you an example. So from A to B, this is shortest path. The intuitive solution is, okay, so next time I remove this link, this path. I remove all the links along this path and try to find another shortest path. But sometimes, O has only one connection. And if you remove this whole link, there will be no connection. There will be no path from A to B. And sometimes you want to find second shortest path, and the result will be of very small variation to the first shortest path. So this is the original path. Then the second shortest path you find is like this. It's from here. It's just taking maybe an unnecessary movement or turning. This is not the one you want, right? You want to find one shortest path like this, another shortest path like that, right? That's the assignment. But how do you do that? It's very difficult. And it has been proved to be difficult. So there are some algorithms already, but they are all heuristics. And we are not going to talk about this today, but maybe in the following lectures. The next thing is called term penalty. So in Dijkstra's algorithm, each node has no weight. The weight only exists on the links, right? But in transportation, we have to consider the difficulty of left turn, because left turn always takes more time. And right turn is easier. Through movement is the easiest. So people are considering this. This is called term penalty or node impedance. But how can we include this in shortest path? Do you have any intuitive idea? Term penalty, using anything we have already discussed, how to address this?
Add some connectors?
Yes, you are correct. So to implement term penalty, we just add some connectors, and connectors have